rule. So we're just going to do some sort of different problem solving today. We're not going to learn a new rule. You do need to get your quotient rule and product rule finished and handed in. I would suggest trying to get that done before we get to the chain rule, which we will likely get to tomorrow or the next day, because then you're going to start to feel probably overwhelmed. Okay, so trying to get them finished today is a good idea. Find the rate of change of the area A of a circle with respect to its radius r. Okay? Evaluate the rate of change of A at r equals 5 and r equals 10. If r is measured in inches and A is measured in square inches, what units would be appropriate for dA over dr? So first of all, dA over dr is just a way of saying the derivative of A in terms of r. That's what it means. Remember I talked about the D stands for differential. It originally would have been a delta, like a lowercase delta. So it means change in A as we're talking about change in R. It's just telling you what would be on the x and the y axis of your slope. Okay, so don't get confused by the notation. The one on top is the thing you're taking the derivative of. Okay, so and the R on the bottom tells you it's in terms of R. So when you want to take the derivative, what you do is you start with your original formula. So if I'm talking about the area of a circle, what is the area of a circle? What's the formula for that? Close. Just pi r squared. Okay? So the formula for the area of a circle is pi r squared. So if I'm doing the derivative here, I'm just taking the derivative of pi r squared. And pi is just a coefficient. Some people get kind of confused when they're doing derivatives like this. They think they have to do product rule maybe or something because it's pi times r squared. But pi is just a number. It's just like if it was 5r squared, right, instead of pi r squared. So all I do is I drop the 2 down and I multiply it by pi. Now you don't actually multiply 2 by pi. You just write 2 pi. Does that make sense? So I drop the 2 down, I multiply it by pi, that's going to be 2 pi. I don't write like 6.28 or something. Okay, you write 2 pi r. Okay, this is the derivative of A in terms of r. Okay, so if I want to figure out the rate of change of A at 5, that means, and instead of writing dA over dr, you could write A prime. If I want A prime at 5, all I do is I plug in 5 for r. And now what would be a simpler way of writing that? 10 pi. So don't leave it like that. That's not very nice. Write 10 pi. Okay, and A prime of 10 would be 2 pi 10, which is 20 pi. What that means is that as the circle here, as the radius is increasing, the rate of change of the area is increasing as well. Okay, like the rate of change, if the area is getting bigger and bigger, faster and faster. Okay, because this is the rate at which the area is changing. And that makes sense because you're squaring the radius. When you square a number that's larger, it's going to get much larger. Now it said, if we know that radius is measured in inches and area is measured in inch squared, this is a little confusing, what would be the units for the derivative? So what you should be thinking about when you're trying to come up with the units for the derivative, you should think about the 2 units. So the units of area are inches squared, and the units of radius are inches. Okay, so you could say, if you wanted to, sounds a little weird, but you could say it's inches squared, or here even, square inches per inch. Okay. Also, just saying inches would be an acceptable answer too. But this actually kind of describes it better. I know it sounds really weird. Like obviously that's equal to inches, because you could just divide. But thinking about it, what it's actually saying is that's the number of square inches that we're increasing by with every added inch. Okay, that's actually the correct kind of answer there. But it is equal to inches. So if somebody put inches, I'd write it. I'd mark it right. But it's confusing a little bit. But it's basically just whatever's on top, so here it's area on top, that's square inches, divided by whatever's on the bottom. So you just write it like that. And writing it as per always kind of helps, like in terms of the understanding. Okay, so that's just a basic kind of problem. Hey, here we have one. This is a quotient rule problem. Find the equation for the line tangent to the curve y equals x squared plus 3 over 2x at the point 1, 2. So as soon as I see something like that, I think I need to do quotient rule, because it's a division, so I have to. And line tangent just means that I need to find the derivative. So I find the derivative of that. What does the quotient rule start with? Does anyone remember the quotient rule from last week? It's been a while. It's f prime g, then what? Minus g prime f all over g squared. So if I do f prime, what will be f prime? X. 2x, yep. And g is also 2x. So it's 2x times 2x minus g prime. What will be g prime here? 2. Thank you, Cyrus. Cyrus is the only one here today. Okay. He's acing it, though. Okay, we have 2. And then f is just x squared plus 3. And g squared means 2x squared. Okay, now if I actually do this out, I get 4x squared minus 2x squared minus 6 over 4x squared. Make sure that if you're squaring something like 2x, you square both terms. I would see a lot of 2x squareds there, I expect. And it would be wrong, so it needs to be 4x squared because you square both of the terms inside of it. Okay, so I end up with 2x squared minus 6 over 4x squared. And to fully simplify that, that's x squared minus 3 over 2x squared. Can I do anything else to that? I can't. If anyone was thinking you could cancel off the x squared or something stupid like that, you cannot. Okay. Okay, so if I want to figure out the derivative at the point 1, 2, okay, what do I have to do? Put 1 in. So I plug 1 into that. So y prime of 1. And I get negative 2 over 2, which is negative 1. So now I have I want to find my equation for the tangent line, so I use y minus y, or sorry, you could use that, but y equals m times x minus x1 plus y1. And you get negative 1 times, and you don't have to put the 1 there, obviously. In fact, I probably shouldn't have, but it's fine. It's there already now. Okay, plus 2. Okay, and that's it. Now, if I wanted to find, if it asked me for the normal line instead, what would I do?
Inverse?
Just the inverse, yeah. The negative reciprocal of it. So the normal line would be y equals just 1 x minus 1 plus 2. Okay, if it did ask for that. Because it often will ask for one or the other or both. Okay, so knowing that the word normal means perpendicular, so you just take the negative reciprocal of your derivative. So this is a very typical type of problem. You'll be asked it a lot on the exam, on the test. You definitely want to be just familiar with it and be able to do it without thinking too hard. Okay, so first and second derivatives, second and third actually, I guess, second and all higher order. The derivative of y prime equals dy over dx. So that's a notation you should be starting to get used to. It's called the first derivative of y with respect to x. But the first derivative may itself be a differentiable function, amazingly enough. So we call it, if we take the derivative of a derivative, we call that the second derivative. Higher order derivatives are denoted as follows. So here's the notation. So you can see y double prime, so just 2 primes. You see here dy prime over dx. I've never seen anyone write that ever in my life, but I guess it could happen. But this third one here is very common. So that means second derivative. I don't really know why the squareds are where they are. to be honest with you. I'm sure there's a reason. I don't know it, though. I think I've looked it up before, but I can't remember. But that's where they put them. They put 1 on the inside, so it's like d2y over dx2. I don't know why it's like that, but that means second derivative. This means third derivative. This means however many derivatives. So you just keep taking the derivative as many times as they tell you. This isn't actually very hard to do. They usually, well, actually it depends. If it's quotient rule and you're doing quotient rule over and over again, they can get pretty nasty, but a lot of the time they're hard. So let's look at a couple here. Okay, like for here, if you just have a polynomial, they actually get easier and easier. So if I'm taking the first 4 derivatives, that means if I'm finding y prime here of this function, y prime is going to be 3x squared minus 10x, and the 2's gone. So y prime is simpler than y, right? Like when you're dealing with just polynomials, that's how this works. They get kind of simpler and simpler. So y double prime is 6x minus 10. Y triple prime is 6, and y, the fourth derivative of y would be 0. Okay? And so they get easier as you go down. It's just you're continuing to take the derivative. So it's like you're looking at the one above it, taking the derivative of it. That's easy, right? Everyone's with me on this? Okay, so sometimes when we get much further into calculus and into this, into derivatives, we'll start seeing curve sketching. The second derivative is really, really important in that. It's also important in velocity questions because when you take position, the first derivative is velocity. And then when you take the derivative of that, which is the second derivative, it's acceleration. So we do end up using the second derivative a lot. It's really important. So taking the derivative of the derivative is something that we will do quite often. When it's polynomials, it's really easy. When it's functions, it can get kind of hard. But we will... we'll get through it together. Hey, here's a word problem. A pretty straightforward one, I think, if I remember. I haven't looked at it in a while. But I bet it's simple. An orange farmer currently has 200 trees yielding an average of 15 bushels of oranges per tree. Excellent. She is expanding her farm. She's a female orange farmer. So if you hadn't realized that, you're sexist. Okay, that's this book is going out of its way here to just defy expectations. You hear farmer, that might not have been what you imagined. I like it. It's interesting. Okay, she is expanding her farm at a rate of 15 trees per year, while improved husbandry is improving her average yield by 1.2 bushels per year. That's a farming word. Okay, what is the current instantaneous rate of increase of her total annual production of oranges? Okay, and it gives us some information, some different functions down here. It says T of x, the number of trees x years from now. Okay, y of x is the yield per tree x years from now. And P of x is equal to T of x times y of x, and it's the total production of oranges in year x. Great. So she has, what is her current instantaneous increase? So she has total production. So we want to do P of x here, because that's the total production, and that's what it's asking us for. So it says in the question, okay, total. Now here what we probably have to do is come up with some equations for T of x and y of x. So T of x is the number of trees x years from now. So right now we're at 200, and we're adding 15 trees per year. So my T of x formula is 200 plus 15x. Does that make sense to everybody that I came up with this? She currently has 200. She's going to add 15 every year. So if it's 1 year, she'd add just 15. If it's 2 years, she'd add 30. If it's 3 years, she'd add 45, and so forth. Okay, so this is the equation for that. Okay, now y of x is the yield per tree 15 years from now. Now it's saying that right now she gets 15 bushels of oranges per tree. Okay, that's her yield. But it's going to increase by 1.2 bushels per year. So that number is starting at 15, but it's going to go up by 1.2 bushels per year. So what would my equation for y of x be?
15 plus 1.2x?
Yeah, that's right. And that's husbandry, it says. That seems like a sexist word, actually, doesn't it? I don't know. I don't really know what that word means. Does anyone know what that word? It means like how good you take care of your farm, right? Haley, look it up. I feel like it means how good you're like taking care of your farm, which is probably like kind of a sexist word. Like it's like it's like your farm. It's like you're the husband of the farm. You know, you're like taking care of your family. It's something probably like that. Anyway, gender studies class. Care of crops and animals.
Care, cultivation, and breeding of crops and animals.
Yeah, I think there's definitely something there to that. We'll find somebody who's an expert in such things, and we'll... Okay, so P of X is these two things multiplied together. Okay, that's what it says. So if I want to find the instantaneous rate of change of this, I need to find P prime of X. Okay, which to do, I would need to use what rule? Product rule. So it's going to be F prime G plus G prime F. So it's going to be 15 times 15 plus 1.2x plus 1.2 times 200 plus 15x. Okay, and that will equal 225 plus, I don't know, 18? Is it 18? Sure. Someone check. Plus 240 maybe. I don't know, I'm just kind of guessing. Can someone like type it in and check?
You mean 180, Callie?
1.2 times 15 is 180?
I didn't see the decimal place.
Okay. I'm like, oh my god. Like, my brain is melting.
It's 18.
It is 18? Okay. But that would be a good way to do it. It's 180 and then you take the decimal. Okay. And then, yeah, so we simplify that and we get 36x plus 465. So his current rate, his current instantaneous rate, I would say it's year 0. So his current instantaneous rate is P prime of 0, which is 465. And what would be the measurement of that? What would be my units?
In bushels, right?
It would be bushels, and this is a rate, so it should be bushels per something. Per tree? I think it's year. So if we did yield, it would be bushels per tree. This one's a little complicated if we look at the units. So let's think about the units here. The units of T is trees. That's trees. The units of Y would be bushels per tree. Okay. So here it's bushels per tree times trees, which would just be bushels, and we're looking at per year in terms of X. So yeah, so it's bushels per year. A bushel is like, it's like 36 cubic feet, I think, or something.
Well, logically you can't have 465 bushels per tree.
Yeah, that would be crazy. Per tree. Yeah, that's a good... So Cyrus said, you obviously are not going to have 465 bushels per tree. That's crazy. That would be like quite a yield for a tree. Like an insanely big tree. So that doesn't make sense. So it must be per year. It is per year. But like, do people follow my thought process on how it's per year? No. Okay, let's look at it a little bit more. So P of X. Okay, P of X, if we look at Y and T, it's Y times T. So it's bushels per tree, because that's what yield is, times times trees, sorry, because that's what one of them is. I don't know, T. So here we have these cross off. Okay, so P of X is just bushels. Okay, everyone with me? Okay, so P of X is just measured in bushels. It also makes sense because it's just the total production, which would just be measured in bushels. Then when I'm doing the derivative of that in terms of X, the derivative, P prime, is, if I'm looking at the slope of that, it would be delta Y, or delta P in this case, over delta X. And X is years, so that's bushels per year. Okay, that's the thought process behind it. It's a little bit complicated, but sometimes you just have to kind of be thinking about it reasonably. If we're talking about the instantaneous rate of change of the total yield is going to be in bushels, and we're talking about years, so it's bushels per year. Try not to overcomplicate things, but This one does make sense, I think. Stop. What time is it? It slightly makes sense. Actually, yeah, we're going to objects moving along. Generally speaking, you're going to just be told it's moving along a coordinate line. So they'll pick different letters for it. Often they use S for position. I don't know why, but they do. They'll often say it's the S-axis. So that just means it's moving like left and right. The displacement of the object is of an object over a time interval is defined as delta S. Okay, yeah. I mean, whatever. That's just kind of obvious. But it's saying here that the average velocity is just the change in position over the change in time. Okay, which makes sense. Okay, so if you drive, 100 kilometers in an hour, you've driven 100 kilometers per hour. Okay, that's how velocity works. Okay, that's pretty straightforward. Ryan, is this new to you?
Has everyone seen that video?
Yeah, I've seen that video.
Okay. So the object's instantaneous velocity is the limit of the average. So basically this is just saying what we've seen before, is that the velocity is the derivative of position. Okay, so we've seen this before, but here's the official statement of it. Okay, the velocity is just the derivative. You're going to be given problems. I like this one here. Okay, so we have there's a picture of a car there. That's a car. And it says velocity tells the direction of motion. Positive means to the right, okay, and negative means to the left. So everyone should know that too. It's from physics and other life things. Okay, so a negative velocity means that it's just moving to the left. So here, if they're asking us for the average velocity from P to Q, we would be finding the average of what we'd call the secant line, so the slope of the secant line. So I know every time we see the word secant, people ask me what it means, because you guys have really terrible memories. So secant is just a line between 2 points. Okay, it's not a tangent line. So it would be like the line between P and Q, that line. Okay, so we're trying to find the slope of that line. So P, it looks like, is 2 and 50, and Q is 5 and 350. So our velocity, our average velocity, would just be 350 minus 50 over 5 minus 2, which is 100. Oh, what a surprise. It's 100. Okay, this is 100 feet per second, though, so it's different. So it's 300 over 3, which is 100 feet per second. Okay, so that is the average velocity of this race car. I don't know how fast that is, because I'm really bad at imagining. I could find out, as could you all, I'm sure. Oh, it's feet, though. I don't know that the change into feet. I'm going to look it up. Who knows, right? Lauren, you're late. It's 110 kilometers per hour. This is like a race car, I think. So that, I mean, it's a race car in the picture. So that's not very fast. I don't know. I guess it's right at the beginning, though. That's only after 2 seconds. So after 2 seconds, it was going like 100 kilometers per hour. That's pretty good, I guess. I don't know. Is that fast?
That's a pretty good 0 to 60.
Yeah. Yeah. So, okay, so if it says average velocity, it just means slope. Now, here's the kind of situation you're going to see. You're going to be given graphs a lot that are you're told are either velocity graphs or position graphs, and then you're going to be asked a bunch of questions about them. So here it says this is a student who's walking in front of a motion detector that records her velocity at 1 second intervals for 36 seconds. Okay, so that's what this is. She stores the data in her graphing calculator and uses it to generate this time velocity graph. Amazing. Describe her motion as a function of time by reading the velocity graph. When is her speed at a maximum? So you're going to have to be able to read these. Usually they'll ask you specific questions. This one's just asking us to describe it in general. But usually you will be asked kind of more specific questions. Now, first of all, I would be thinking about the scale. So this picture, it tells us that it's up to 36. So if I count, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means each one of these little ticks represents how many seconds?
3 or 4.
It is 4. Thank you, Haley. 3 or 4. It is 4. Okay, so this is 4, 8. That looks just like an 8. Okay, 4, 8, 12, etc. Okay, so we have our graph moving there. We are at the beginning. What most people do, the problem that most people run into is that they just read this as if it's a position graph. So I get a whole bunch of people reading it. They're like, okay, well, they're moving. They go right, then they go left, or like, I don't know. They do weird stuff. Like, it's like, oh, she's moved far away, and they're just describing it as if this was straight up her position. This is her velocity. So when her velocity is positive, which it is up until here, okay, that would be 12, between 12 and 16, so 14, I guess, at about 14. It's positive that whole time. So what direction is she moving? Right. So for the first 14 seconds, she is moving right. Okay, and that you have to be able to read that and say that there. So she starts off moving very slowly and moves faster and faster. That's how you should read this. Okay? She reaches her maximum velocity up here and stays at it for those 4 seconds. Okay? So she's like speeding up. She's accelerating. Okay? At first she's accelerating. Then she reaches her maximum velocity, which we could find out if we wanted to, because it says it goes to 7.5. So each one of these is 1. So it's like she's getting to a speed of 4 meters per second or something. Okay, but then she deaccelerates. Okay, as she's coming down here, she's deaccelerating. She's not moving backwards. She's not moving left. Even though the graph's going the other direction, she's not moving left. She's just slowing down. As long as it's positive, she's moving to the right. So I would say in the first 14 seconds, she moves right. Accelerates until 4 seconds. Remains at a maximum, at a max velocity. For 4 seconds, then deaccelerates until she stops at t equals 14. Okay, so something like that. You're just describing what's happening. So she stops at t equals 14, then what does she do?
She goes left.
She goes left, and is she getting faster or slower as she goes?
What?
She slowly gets faster.
She's going.
Down here, it's really low, so she's going really fast. Okay? So she's going really fast, and then she slows back down to here. Okay, so that's 16, 20, 24, that looks like 26 or so. So you write the same thing. She's going left. She accelerates and deaccelerates until 26 seconds. And then after that, what's happening right here?
She goes backwards.
Doesn't move.
She's not moving.
Oh, is that completely flat there?
Yeah. Okay, and then she goes right again, quite quickly. Okay, she's accelerating. So the question, you write all that down, I mean, if you had to. But the question here, the big question that we are asked to answer is, when is her speed at a maximum?
At the minimum of the graph.
It's actually at the bottom, that's right. So speed, and I will say this a lot this year, and a lot of you will ignore me. Speed is the absolute value of velocity. Okay, so it doesn't matter if it's positive or negative, your speed is always just positive. Okay, speed is a not a vector. So you just always make it positive, okay, all the time. So here it would be either the lowest or the highest point. Now, since it gets lower than it gets high, it's that bottom point. So that looks like it would be at 20 seconds. So 20 seconds is where the speed reaches the maximum. Okay, so you need to be able to read these graphs. People, it doesn't seem that hard, I assume, when I'm doing it up here, but generally speaking, what people do is they just read it as if it's position, and they get the questions wrong. So be really, really clear with yourself what you're looking at. It always will say in the question, like, this is a velocity. It's usually a velocity graph. It's going to be pretty rare that they give you a position graph. So you should always be expecting a velocity graph. Now, acceleration, like I said yesterday, is the derivative of velocity. So that makes it the second derivative of position. Does that make sense? Okay, so just thinking about it kind of logically, right, like we talk about the way that slope works. So if we have a position time graph, so if we have time and position, let's just do meters and seconds. So it's meters and seconds. Okay, then the slope of that is meters per second, which is its derivative, which is obviously velocity. So then we have velocity time, which is also in seconds. So if we take the slope of that, it becomes what? Meters per second squared, or meters per second, which is acceleration. So that's acceleration and time.
That is funny that it's so much easier explaining this.
Yeah, you could do derivatives with physics. So I mean, I don't know if you're allowed to in class, like, but you can do it. They will work. You have a question? Sorry? No, you're just stretching. Okay, so here's some just quick facts for you. That gravity is 32 feet per second squared, or 9.8 meters per second squared. But don't worry about that. I don't think I have that require you to know it. So let's just do one question involving velocity and stuff. So a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 106t minus 16t squared feet after t seconds. Okay, so how high does the rock go? So here, if you didn't have a calculator, okay, let's imagine that for a second.
That's scary.
Let's just imagine a world where there's no calculator. Okay, so this graph is a parabola, right? So that graph looks something like, I could imagine, I could factor this. I could factor out a t. Oops. Okay, that graph is going to look like this. Now, at a maximum, because we're doing calculus, I'm not asking you to do something. Finding the maximum point in your calculator is something I would have asked you in grade 11 math. Okay, so I'm not going to ask that. I'm going to expect you to do it using calculus. So at the maximum, which would be right here, from the assignment we did yesterday, what would the derivative equal there?
0.
0. So all I have to do for calculus is take the derivative of this and set it equal to 0. And it also makes sense. When something reaches its maximum, like if you launch something straight up in the air, at the very top, its velocity is going to be 0 for a second. Or not a second, but for an instant. Because it goes up and its velocity is positive, then it's going to have to be 0 before it drops. Okay, that's how it works. So we're going to have a velocity of 0 right at that maximum point. So we find velocity. So velocity is 106, take away 32t. Okay, is everyone okay with that? And I set that equal to 0. Okay, and I solve for t. Okay, so we weren't all okay with it. I took the derivative of 106t minus 16t squared. Okay, so okay, so we just do the division, and we get that it's 3.3. Okay, so t is at 3.3. Oh, yeah. So that's the time that it reaches. Doesn't seem right. It must be. I mean, this was 3.3. Oh, yeah. Sorry. Yep. It's fine. That's supposed to be 16. That's why. I was looking at my, like, bad factoring. Okay. So it's 3.3 seconds, which is fine. Now, B, it says, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? So we have the velocity formula. Okay, the velocity is 106 minus 32t. But we don't know the time. That's not given to us in that problem. It just tells us that it's 56 meters. So what do we have to do? Or 256 feet, sorry. We have to figure out what the time is. No. I don't think that would help. How would that help? Does someone have an idea for something?
Well, if we do the second derivative, that would be acceleration, right?
Yeah.
And so can't use acceleration to find time?
I mean, acceleration here is just going to be gravity. It's just going to be negative 32. Because it's just a free fall. Yep.
Wasn't the first question asking for height rather than time?
Oh, yeah. How high does the rock go? So we should figure out how high it is. You're right. Thank you. Okay, so our position, S, is 106 times that 3.3. I wouldn't use 3.3. It was a bigger decimal than that. I'd use the whole thing. Minus 16, 3.3 squared. So our position at that point, 106 minus 16 squared is 175.6. Oh, well then that question's really stupid. It never reaches then. If the maximum's 175.6, it's like, what's the speed of the rock when it's 256 feet above? It's never going to be that far above. So that question's really easy. Let's change it to 156, because I'm assuming that's what it was supposed to be. Okay, so if it was 156, what you have to do first is figure out what the time is. So you just put, that's the position. 156 is the position. So you just set that equal to 106t minus 16t squared and solve for t. Okay, and I would say you'd be using a calculator for this, pretty much for sure. You could try to factor it. I just changed the number to 156. Okay, I would just use a calculator though. For something like this, because it will be a decimal. Now, what would I set my windows to if I was trying to figure this out? What would be a reasonable thing to set my x-axis to?
Probably 5.
Yeah, or 6 or something. Like, if halfway is 3.3, I'm like, this is going to be 6.6, right? So, maybe more than that. But to be honest, probably 5 would work. So then my upper windows, I know the maximum is 175, so I'd probably set it to higher than 175, like 180. Okay, and so then I get, oh yeah, there we go. I get a picture that looks like this one, and it has the 156, like right here. And so it wants to know what is the velocity when it hits it here and here. Well, I know what it's going to be the same velocity, just one will be positive, one will be negative. Does that make sense? Because it looks like kind of like it would be a mirror image situation. So on this side, the tangent line would be like this, on this side it would be like this, but they'd be the same slope. It would just be one negative, one positive. So I just find out what those t values are in my calculator, use the intersect button. It's 2.2 and 4.4, and then just put those into my velocity formula. So my velocity formula, which I already got, my velocity, so I want velocity of 2.2, I just plug that number into the formula, 2.2 minus 32 times 2.2. and you get 35.6. So then what would the 4.4 be?
Wait. Where are you putting the 2.2?
Into the formula for velocity that we got earlier. So we got a formula for velocity earlier. That's 106 minus 32t. Okay, so I'm just using that formula. That's a derivative formula that we got. And now if we plug in 4.4 into there, I don't even need to do it. I know it's going to be negative 35.6. Okay, because it's on the opposite side. So the speed at both points is what? 35.6 feet per second. Okay, and finally, question C. When does it hit the ground? You don't really need to use any calculus for that, probably, because you should be able to use some common sense instead. If the maximum was at 3.3, when will it hit the ground? At 6.6. Okay, using that famed common sense. So generally speaking, on these problems, if you're asked to find a maximum or a minimum, what you do, this is like just an important thing, if you're asked to find a maximum or minimum in calculus, you find the derivative and you make it equal to 0. Okay, we're going to be doing a lot of those problems eventually, but it makes sense because at the maximum or minimum, you always have that horizontal tangent line. Everyone seems to be getting that because on the assignments, you don't seem to have any problems with it, so